Hello Noddies, welcome back to our YouTube channel. In the previous videos, we saw RC low pass filters, high pass filters, and transient response. Today, let's look at the RL transient response and understand something really interesting. This is a circuit. We have a resistor and an inductor connected in series, and the output is taken across the inductor. Before looking at the equations, let's first understand what the inductor is trying to do. The golden rule is an inductor opposes any change in current, not voltage, but the current. Keep that in mind throughout this video. Now let's apply a 1 volt step input. At the exact instant when I try to apply the voltage, the current wants to jump from 0 amps to some finite value. But the inductor says, hold on buddy, current cannot change instantly. So at initial time, the inductor behaves like an open circuit, no current flows through it. Since current is 0, there is no voltage drop across the resistor. And if there is no voltage drop across the resistor, where does the entire voltage shows? It just shows across the inductor. So that's why initially V out is equal to V in and the current is equal to 0. Now let's move forward in time. Let's say the inductor has attained its steady state. As the current increases, voltage begins appearing across the resistor, and because the source voltage is fixed, the voltage across the inductor starts to decrease. Eventually, after a long time, the current became constant, which in our case is VI by R, which means the inductor voltage becomes zero. So in steady state, the inductor behaves like a short circuit. Now let's try to verify it mathematically. So before that, these are some of the important formulas that we have to consider before designing our circuit. Now let's assume our Vin is 1 volt, R equals 1 kilo ohm, and let's just say we want the current to settle at 5 microsecond. So we have to find L accordingly. Here we are going to take 5 microsecond is equal to 5 tau. The reason why we are taking 5 tau is at 1 tau we can say the inductor is charged to 63 percentage, and at 2 tau it is charged to 86.55 percentage. So around 5 tau it is charged to 99.3 percentage, which is nearly 100 percentage. So that's the reason why we are taking 5 tau. Here we are inputting 5 tau and the tau value is nothing but 1 microsecond. Here tau is nothing but L by R. So substituting the R value we get L is equal to 1 millihenry. Now let's look at the waveform because this is where things became interesting. Notice the voltage starts at 1 volt and exponentially decays to 0. That actually makes sense. The inductor is slowly giving up its voltage as current builds up. But now watch carefully. When the voltage waveform suddenly falls from 1 volt to 0, something strange happens here. The output suddenly goes to negative 1 volt. Why? The reason why this is occurring is just think about the current. Just before the falling edge, current is flowing through the inductor. The source suddenly says, okay, stop the current. But the inductor says no. Because as we know, inductor cannot change its current instantaneously. So to keep the current flowing in the same direction, the inductor creates its own voltage and the polarity of the voltage is opposite to before. That's why we observe a negative spike. The main thing to remember here is rising edge, current rise to increase, positive spike. Falling edge, current rise to decrease, negative spike. And that's the entire intuition behind RL transient response. So now let's try to simulate the circuit. Open your cadence, press I on your keyboard to open the add instance window, click browse, go to your analog library, find your resistor, place your resistor, go to the add instance window, find your inductor, and our inductor is found out to be 1 millihenry. So place your inductor, find your voltage source which is V pulse, give your input voltage as 1, your period as 20 microsecond, and your pulse width as 10 microsecond. Place your voltage source, press W to wire your components. Before that, press R in your keyboard to rotate your resistor, press W to wire your circuits, press I to find your ground from the instance library, place your ground, and press W to finish wiring your circuit. Click check and save, launch ADL, choose analysis as transient analysis, and fix the stop time as 50 microsecond. Click OK and choose the input node, output node, and the red dot here to find your current across the inductor. Press OK run your analysis, separate your graph. So at the 1 volt we get a 1 volt spike, and at the 0 volt input we get a minus 1 volt spike, and we know the inductor gets charged at 5 microsecond. So we could see around 5 microsecond the inductor is charged 996 microamps, which is near to 1 milliamp, which is V in by R. Our V in is 1 and the resistor is 1 kilo ohm. So we get around 1 milliamps current across the inductor. We have successfully designed and simulated our RL transient response, and these are the some of the circuits that you can try it yourself. Here tau is equal to L equivalent and R equivalent. So basically you have to find the L equivalent and R equivalent, and rest of the calculations are same. Thank you, Noddies. We'll see you in another video.